Hello everyone, I will present a digital backend design for Argos. It's related corresponding to the work page 3 and work page 6. First, please meet my colleagues. So I'm working in the backend development group led by Yuan Ba in the Institute for Radio Astronomy. And we design backends for various telescopes such as Atmosphere, of course, and also for Meerkat, SKA, prototype dish, and the Thailand radio, national radio dish telescopes. And we build them, we design them out of commodity off the shelf hardware. Commodity off the shelf means that you can just buy it in the supermarket almost. And then our major focus of development is in the UD system. That's the Atmosphere direct digitization. Obviously, contrary to the name, it actually works in different kind of telescopes, either from like be working on the Atmosphere SK prototype and the Thailand with the accelerator dishes telescopes. And so we'll give you a more about the ED system that includes the Atmosphere. In the blue box are the backend components. It includes the ADC, the packetizer, the networks, and the itself, general servers, GPU, jigs. And in a more in the perspective of physical architecture, you already seen the slide from John. Each receiver has a digitizer, connected to the packetizer, and then also connected to the GPUs and DJ servers via Ethernet networks. And the GPU and DJ servers connected by to the storage servers through the Ethernet networks. So this is the physical architecture for the ED system. And on the software part, we build the software stacks all the way from deployment to the storage management. The best things about this software stack is they are already running in Atmosphere, in SK prototype dish, and Thailand National Radio Telescope, and they are being actively developed and maintained. So we can just use it directly on the Argos, because we are also using a similar commodity of the servers. And then for this EDD systems, we in the Argos specifically we supported various types of science, like the type of domain science, like also timing researching, and also for the specialized speed and also the OBI observation. So this is the interface of monitoring the EDD system. Okay, so this is Atmosphere, and we are here to talk about Argos. So let's see something decide about Argos. So this is the proposed physical architecture for the backend for Argos. So for each dish, after the analog front end, we have this Argos software that carry out all the digitization, visualization, and digitization, and then transfer this channelized and digitized signal to the GPU and FPGA servers via Ethernet network, and also similarly connect to the storage server like servers. And these servers are all implemented by off-the-shelf servers. So it's pretty straightforward architecture. Before we go more detail in the RF software, we also want to talk about like this beamformer that we also include in the backend design. So beamforming is to coherently combine gain from multiple receptors to different directions. In Meerkat, we use the configuration of the antenna, and the location source to simulate the horse back function so that we can categorize the body shape of the instrument. Then we try to tie it on the sky. Optimal, you can see here we tie the timing according to the overlap level or the gain level of the PSS. And this is the timing on top of the 47 task region, and these parcel profiles are came from the beams only directed to and with this technology that we have few advantage. First, we can with small dishes we can get a large field of view, and also because we form beams, so we have very less pixels than from the imaging, so we can get a very high time solutions like we can get down to microseconds and also sometimes even nanoseconds. Also, it's in topology, so we can also have a very good spatial resolutions. When we detect a source in these beams, we can immediately localize them within maybe 10 seconds. And then also, if we get multiple detection, we can also even further, further localize to down to like 12 seconds. So it's a pretty good and working solution for Meerkat. So since 2019, we have already discovered that 220 new pulsars inside the chopper project with Meerkat. We also discovered a few other pulsars and FRBs to other projects with Meerkat. So this is the information we will likely include in the backend. Yeah. And then we go back to Argos. The requirements for the backends are like session implementation, and also perform people correlation. And also we also do this time domain processing for pulsars, pulse chains, and other time domain sources. And in the meantime, we provide infrastructures for science processing by imaging, post-processing, converting, and also provide inputs for monitoring and control of backend hardware. And the GI and also the department of this decides that it needs to be cost effective because for the past fighter we have limited budget, versatile, so all kind of science, and crucially we need to scalable because eventually we would like to use similar design tool in the full Argos array. So let's get to the magic. You can just look at the big words. So the backend include the management servers, the digital enclosure, the front-end enclosure, and have enough digitization and all when achieved by the export port. And also we have these people made by the data servers and kind of sensors and sensors that are hosting this general purpose the off-the-shelf servers. So connect them with the network and network to the storages. We can provide each model in detail. First, the digital enclosure, and it also contains the analog function and can provide the connection to board to carry out this presentation and then the channelized digital signal will transfer to the GPU and G servers while it's in the network. And we can look into more detail in this part, which is using the Argos board. There's a lot of different FPGA board in the market. We choose the Argos board because it's like other than it's very powerful, because it also contain exactly the interface we need. So Argos board is our board container EAC on one single FPGA, and then this Argos board is just like kind of curate this interface that already ready for use for the applications. And for our applications, it's crucial that it contains that 5 gigabit per second ADC, which are automatic calibrated. So we don't really need to worry about synchronization. The temperature control is already done at the board. And the second one is that the 100 gigabit for small form factor demo interface we use to connect using fiber to the GPU and G servers, GPU servers. And we will use one board for antenna and use dynamic sampling without mixing and channelizing. And then the final product is that tool we produce two simultaneous dual bands from 1 to 2 gigahertz and 2 to 3 gigahertz. We get the detail that next slide. So this is the image. This is the animal format. This is the digital front. Animal format we will know more about in the next talk. This is placeholder. So after the LNA, we get to the ADC or the Argos board. This is how the Argos board. That the analog signal goes through two anti-aliasing bandpass filter. One is 1 to 2 gigahertz, the other one is 2 to 3 gigahertz, and then inside the ADC, we use a sampling of 4 gigahertz with decimator of 2. So the effective sampling is actually 2 gigahertz. And then the signal, the surface signal from 1 to 2 gigahertz and 2 to 3 gigahertz will be folded back in the language zones under sampling techniques. So then after the AD sampling, we will get this upper band magnetic signal from 1 to 2 gigahertz and the lower band from 2 gigahertz and upper band from 2 to 3 gigahertz. Using this size, we remove the necessity of the down converting components which will not only synchronize the single chain, but also reduce the cost of system and introduce less noise. And it's already we have been using this in the system. So using different hardware. So about the beamforming correlator, as I mentioned before, beamforming is beamformer responding for creating tilings, generate geometric weights, so that we can form coherent beams and also form incoherent beams with way bigger field of view. And correlators, which also detail in another talks that they calculate the abilities. The backend is hosting these correlators that we not managed by us. And then similarly, we have the data processor, one is tied to the processor, which are equal to the backend design. And in this type of processor, We do passive time observation and also search and installation. So it's commodity off-the-shelf service, so we can install all kinds of software we normally use for the parser strongly, like PS Archive, Pesto. You can just do and work with servers. And we also call beamform baseband database one more features. And the science processor we are open hosting it, and it will be managed by Workbench 7. So in the grants, we have all this hardware in the backend. We have 6 other support. We have 4 GPU, CPU servers with 4th generation AMD CPUs and then now L40 NVIDIA data center GPUs, and we have 1 terabyte of RAM to also have 200 Ethernet interface and then for the storage server. And storage server we have about 1.6 terabyte data storage capacity, and we have a magic server for the system to monitor and control the whole backend. And we have cables, switch for all kinds of connections between the servers and antennas, and converters between the signal digital signal either from antenna or server. And then in highlight of this backend design, and currently we are doing system engineering, making schematic and writing interface control documents so that we can settle how we communicate with the other components in, like for example, for the slides processor and from there. And then we also already designing the channelizer firmware. And next year we will probably start purchasing the equipment, and in the further time, like maybe late 2024 and 2025, we will try to start to deploy the server, then start commissioning in 2025 with the prototype Argos. Yeah, so it's
thank you for the overview. Synchronization of the multiple horizons.
You mean the synchronization? Synchronization of sorry, can you repeat it?
Of the digitizers.
The first, we will use there's this beamformer which will calculate the geometry way, so we can already collect some delays of the translation, and then after all of that, we will have this calibration using the calculator to generate some instrument weight instrument solution for the delays, and also apply to the channelizer. So when they channelize and take output to the other servers, or face up.
Signal to all the components?
I think this the clock signal. I think this we can input the timestamp into the backend part, the other support, but we haven't get into this part yet. But if you have any suggestion.
Yeah, I can. People can hear me. Hi, everybody. Yeah, we didn't have this in any stock, but we do have a time frequency reference distribution system which we built for Meerkat, and we have another one for we have several for Ethelsberg, in particular for the new cryogenically cooled path that we're developing. So we will have the clock signal being distributed through that board, which will then send out the same 1 PPS and 100 megahertz to all of the RF soft boards, from which we can then synchronize. And we can measure round trip delays on those as well.
Other questions?
Yeah. To really understand what exactly you mean by channelize, what does a channelizer do?
So here, after ADC is still a time, is like a time stream, and to do this improper, to do like time domain science, or for example, to do the dispersion in when we parse data, we will channelize data, and that because that we can perform like if we have more channel or frequency resolution, we will disperse it more correctly. You are asking the purpose of the channel is to turn the time domain signal, the time the raw voltage into multiple data stream of different frequencies using a polyphase bank filter.
Yeah, so it is function performed by the SDR code.
Yes.
Okay, yes.
Right. Other questions for Weiwei? Oh, there's a hand by. Okay. So, Yanni, please go ahead so we can unmute yourself.
Yeah, sorry, I don't know if you can hear me well. Maybe I missed the information, but what is the forcing bandwidth for the Argos receivers? That's one question. And for the backend, would it be flexible to accommodate larger bandwidths, for example, in the future? Or so looking further away in the future? That's my question.
Yeah. So what's the so basically the frequency the target for the frequency range is 1 to 3 gigahertz. For now, that's what we designed the FITs
yeah, for the current design, the current Argos support bandwidth of 5 gigahertz and 7, and we use a designator of 2, so the effective separation is 2 gigahertz, and if the analog signal can support higher frequencies, and then we will of course can use sample rate of 4 gigahertz, and we can support more frequency, more higher frequencies. But then we have a larger data rate, and we will add more servers. But I think that's definitely viable.
Okay, thanks.
Can I just make a comment to that? The RF soft boards that we're discussing at the moment for the Pathfinder, which obviously wouldn't necessarily be the same boards. It certainly wouldn't be the same boards as for a full scale array. Only have a single QSFP 28 100 gigabit link on them. So that is currently the cap for the bandwidth that you'll get out of the receiver. You can do more digitization, as we said. The digitizers actually can go up to 5 gigasamples per second. But getting that data out of the RF soft board is the challenge.
All right, thank you, Jan.
Right, and I think there's a question.
Yeah, so regarding the first question on synchronization, the boards have inputs for external clock and PPS. So as Johan said earlier, there will be a central clock, and we will distribute the clock signal to all the array. And each RF sock will be in sync with all the others through this single clock. So
Yeah, there will be another module at the funding that generates the BPS and on the district. I'm assuming.
I think directly the clock signal will come in the form that would be the proper form for the RF sock to accept. So there won't be an extra hardware at the antenna. The clock signals will go directly to the RF sock.
I'm not sure that's true.
Okay.
There may be because I believe the RF sock boards don't take an optical line, and we will have an optical transmission of the clock. So there will probably be a converter module in the front end box, but that's still TBD.
Any final question? If not, we can